An amplifier with T network in its feedback path as shown here is constructed using two op-amps. As you can see, the first one is a buffer scheme op-amp which doesn't do anything, is this V2 is just copy pasted to here, and the second op-amp is amplifying V2 and V1 to output. We want to show that the relationship between Vout and input V2 and V1 is governed by this formula. A very quick way to do this is thinking about the problem using the superposition, because we have two input independently, we have two input voltage at input. Let's just focus on V1, and to do that, according to superposition, we can set V2 is to 0 as if it's not there. If we do that, then it is as if the voltage at the positive terminal is 0. We make the assumption that the supplies, the positive and negative supplies for the two op-amps properly applied, so that we can assume op-amps are biased properly and virtual short is valid. Since virtual short is valid, therefore, assuming op-amps are linearly operating, therefore the voltage at positive input terminal for op-amp should be equal to voltage at negative input terminal for the op-amp. So if we have 0 here, then we should have 0 here as well. So knowing that according to superposition I set V2 equal to 0 and I'm focusing on V1, the circuit looks like this then. So my circuit then looks like just V1, and you will see that I have R1, and then I have just one op-amp, and in a negative feedback loop, and the positive is just grounded because there is nothing coming there, AC ground. And then I have R2. As you can see, I have effectively R3 to AC ground, and then I have R4 to AC ground, and then I have R3 going to the output, like this. Okay, so how can we deal with this scenario or this design or circuit? The best way is just quickly, now that we know virtual short is valid, so here is 0, therefore here is 0 as well. So the best thing I can do is I can just go ahead with simple KCL. So what's going on is something like this. If there is a current that is going from output, this current will end up going to R4 and also going to R2 and continue going to R1 like this. Okay, so let's name this node here, the voltage of that node, let's name it Vx. So using just simple KCL, since I can write V, obviously as you can see from V1 to Vx is just an simple inverting scheme, but let's write it Vx minus 0, which is Vx minus 0 divided by R2. That's the current going through R2. I am talking about this current. Should be equal to 0 minus V1 divided by R1. I'm talking about this current. So these two currents should be equal. And the conclusion from these is what is well known, which is Vx over V1 is equal to negative R2 over R1. That is effectively the gain of seemingly inverting amplifier that we see between V1 and Vx. Now, keep this as equation 1. But that's not the only KCL we can write. I can write a KCL from Vout as I am showing here. So I can write a KCL from Vout through R3, and then should be equal to two current that I'm going to show in different colors so that it's visible. So it should be equal to these two current, one going through R4, the other one going through R2. So what is that KCL? Let's write it. So that KCL is Vout minus Vx divided by R3, so that's this current, should be equal to Vx over R4, which is the current through R4 to ground, AC ground, plus Vx minus 0 divided by R2, meaning the current that is going through R2 toward the negative input terminal. Okay, so if we clean this up, we will see that Vout becomes just as simple as Vx times 1 plus R3 over R4 plus R3 over R2. Great. So we found Vx as a function of we found Vout as a function of Vx as equation 2. Now all I need to do is I just need to substitute Vx. So remember what I found here? Let me just write it in another way so that it's clear. So basically what I found is Vx is negative R2 over R1 V1. So now I am going to combine equation 1 and 2. So combining equations 1 and 2. Okay, so combining equations 1 and 2. Basically I am going to, in equation 2, I'm going to substitute Vx using equation 1. So what I'm going to get is Vout, okay, so is Vout equal to negative R2 over R1 times 1 plus R3 over R4 plus R3 over R2 times V1. Okay, if we just do a little bit of a cleanup by multiplying R2 over R1 and pushing it inside, just finish the algebraic work, what we're gonna get is as simple as this. Negative, so I'm gonna keep R1 outside for let's put it this way. I'm gonna keep R1 here, and then in the numerator, if I'm writing this whole thing properly, I'm gonna get R2 and plus R3 plus R2 R3 divided by R4 times V1. So what is the significance of this? Well, it's very similar to what we are used to see. So we have Vout defined in this formula as a function of V1. So effectively, and be careful of that negative sign. So what we found is Vout over V1. Let's keep it that way. It's fine. All I'm trying to say is what we found effectively is Vout is negative some resistor of T network divided by R1 times V1. That's exactly what we, in summary, obtained. What is the beauty of this? Well, if you remember from the design of, let's say, inverting amplifier, if you have a simple scheme like this, so positive input terminal, let's say AC grounded, and negative input terminal, let's say connected via R1 to some V1, and you have from here some RT or some resistor that is connecting the input to output in a feedback mode, and Vout. We know then for this circuit, which is referred to as inverting amplifier, the gain or the relation between Vout and V1 is defined like this. So effectively we managed to find some equivalent, let's say, resistor for the feedback system that we have here. Now, the nice thing is we don't need to repeat this for now the other scenario in which we are going to use the superposition by setting, let's say, V1 to 0 and by activating V2. We don't need to do that because effectively if we do that, what we're going to end up is V2 of course appear at the output of the buffer as expected, and the scenario we're going to have in our design will look like something like this scenario. So we will have this minus plus when we are doing superposition and putting effectively V2 on the positive terminal. Then we will have R1 and then ground, AC ground effectively, and then I'm not going to show the T network. I'm going to show RT that we found. So, and then Vout. Well, this is what is referred to as non-inverting amplifier using a simple op-amp, and it is well known that the gain of this circuit is simply V out is 1 plus RT, or whatever equivalent resistor impedance you have in the feedback network, and then divide by R1 times V2. So we are done, meaning that I just found that for the scenario that V1 is activated, I get this. For this, and V2 is shorted. For the scenario that is the other way, I get this. So from these two, when combine them together, I get V out equal to, as you can see, I have negative RT over R1 V1 and I have RT over R1 V2. So when I combine them together, naturally what I get is RT over R1. So let me just write it in a better way. And I'm going to take care of another parameter that is remaining just a bit. So RT over R1 V2 minus V1. Okay. And one last thing that is remaining is I didn't take care of this 1 times V2. So I need to put it here as well. Okay, that's it. We proved it. We're done. That's exactly the outcome that I was trying to get to. As you can see, please compare that to what we were planning to prove, which is this thing. So if you compare, you can see that I exactly have V2 plus the delta of the input voltages times RT over R1, where in the formula that I'm showing, this whole thing is RT as I just told you. So you end up with as is shown here. There you go. I'm just trying to show you. So the RT is this thing. This is RT. I just named it so that I don't need to rewrite it basically, but we just proved what was needed. So that's the final outcome. I hope that this example is helpful to show you how you can, in a quick fashion, using superposition and also just KCL, how you can find the voltage gain for a sort of a differential amplifier that has the T impedance or T resistance in its feedback loop.